Well, hello everyone. We've got a great turnout today, and it's a real pleasure to welcome you all to today's webinar. My name's Tim Morris. I'm going to be host for this event. In my day job, I'm the Chief Executive of Nathans. We're a not-for-profit organisation, and we've got the goal of promoting more effective use of engineering simulation technologies. So the subject of today's presentation is going to be of great interest to me. I'm also here because I'm a member of the Structural Technologies and Materials Group of the IMechE. I'm really delighted to be able to introduce this event to you. The format of the event is that in a moment, I'll introduce you to today's speaker, David Pani, and then I'm going to hand over to him. He's then going to make his presentation. That's probably going to last about 20-25 minutes, and then we'll open up the floor to questions. You can submit questions at any time during David's presentation, as well as at the end. I'm going to read out the questions to him after he's finished his presentation. But please don't feel the need to wait until the end to submit those questions. Just type them as they occur to you, and then we'll get to them at the end. So I'd like to introduce today's speaker to you. Dr. David Pani is JCB Group Structures Manager at JCB Group Engineering. He's a chartered mechanical engineer, and he's a fellow at the Institute of Mechanical Engineers. And for the past 14 years, he's been responsible for JCB structures across the globe. He heads up a core team of stress engineers who support the global business with technical expertise. Dave's going to share some more details of his background with you during his talk, and he's going to be speaking to us today about welding simulation to optimize the design and development of off-highway construction equipment. David, over to you.
So, good morning to you all, and it's a pleasure to speak with you today and to share some experiences with welding simulation in the off-highway vehicle sector. Now, the use of arc-welded steel fabrications has proven itself durable in this industry over many years, and there is considerable qualitative experience in selecting correct welding parameters. However, the process of designing fixtures, optimizing weld parameters and validating them is a highly time-consuming, iterative and therefore expensive process. More recently, simulation tools have become available to help design and manufacturing engineers optimize their design at an early stage in the process to reduce that cost and time to market. Now, this presentation is going to outline the historic process of proving out fabrications and then give some case studies, which I hope you'll find interesting, where upfront welding simulations have been successfully used to optimize the weld parameters to reduce distortion and improve weld penetration, whilst at the same time reducing the physical testing that's required. Now, a quick word of warning. This is not going to be a highly technical presentation. There are no equations in this, so please don't ask any challenging techie type questions at the end. However, a lot of the case studies that I'm going to present today have been done by colleagues in India, and if all is well, I'm hoping they should be here at the end of this presentation to help join in the discussion and answer any questions. And finally, before I start, we have used a particular software tool called SysWeld, but I should add other tools are available, and I'm not here to specifically promote any particular tool. So, without a delay, who am I and why am I here? I'm a structures or stress engineer at heart. I started my career with JCB in 2001. Having completed my PhD designing and developing carbon fibre components. I started at JCB full-time in a structures design and analysis role, working on welded steel fabrications for compact or small telescopic handlers, skid steer loaders and compact backhoe loaders. I then moved into a development role, testing those very same structures with strain gauges and rigs to see if my designs were actually as good as I thought they were. I quickly realised that the strain gauging, rig testing and the simulation activities all gave different perspectives. None was right or wrong. Good, robust, well-correlated simulation models do not happen overnight. They take time and experience to develop. The best way to build that experience is just to take some brave pills and start using them. Currently, I head up global group structures, and I'm responsible for the process of structural design across the global JCB group, working with a team of engineers developing processes and products. Increasingly, the simulation tools that we use are interfacing with other systems and disciplines such as manufacturing, where the benefits of process simulation are more recently starting to be understood and unlocked. And in the past 20 years, I've seen simulation technologies mature. Most of my experience is with the structural FEA, which is often the most mature discipline in many companies I've found. But having seen the benefits of simulation firsthand, I want to champion them, hence the quotes that I've put up here. I am passionate about supporting the global business to produce efficient, durable structures using a pragmatic combination of simulation and physical testing. At this point, I really would like to acknowledge my colleagues from India who have helped us introduce weld simulation into our toolkit. Mr. Nankishore Karande, who is our subject matter expert for welding in India, and Mr. Santosh Shade in the simulation team. Together, both have helped make weld simulation a reality. Now, I hope most of you will be familiar with JCB. The company was founded in 1945 in a small lock-up garage in Uttoxeter by Joseph Cyril Bamford. Those of you who are on the ball this morning may have already figured out that this is our 75th anniversary year. In that garage, the very first JCB product, a tipping trailer, was constructed largely from welded angle iron and box section. 75 years later, we are a global organisation and ranked in the top 3 construction equipment manufacturers. You can see the scale of the organisation in figures from 2018 here. The turnover, 4 billion, 96,000 machines produced. We use a lot of steel, 0.4 million tonnes of steel and 3,000 tonnes of welding wire. I'll let someone smarter than me do the maths and figure out the length of the wire that equates to and how many times that would go around the earth. We are generally welding up thick gauge material with plate thicknesses typically in the 6 to 12 millimeter range, and the welding is a combination of manual and robot metal arc. So hopefully you can see that right from day one, welding has always been embedded deep in our DNA. Now I want to give you a feel for the range of products that we produce. Most of these are made from welded steel fabrications produced in-house, all of which require tooling and weld procedures to be developed. The range is extensive, over 350 different models. Products include the iconic backhoe loader that you can see here, telescopic handlers, wheeled loading shovels, excavators, skid steer loaders, dump trucks, you name it. Now these tend to be split into 3 main weight ranges. The compact, which are machines up to about 8 tonnes. Mid-range is generally 8 to 14 tonnes in weight, and heavy line is everything above 14 tonnes going up to about 50 tonnes. And then the other range that we can see at the bottom is other less mainstream products, such as engines, generators, industrial forklift trucks, etc. We develop and produce the machines and fabrications around the world. The focus of the organisation is in the UK, where there are 7 machine business units and 5 component business units providing parts. The next focus is in India, where we're headquartered in Delhi, but we also have significant manufacturing and design capabilities in Pune, and India is a very important market. In China, JCB China operates out of Shanghai. JCB Inc. manufactures from North American market in Savannah, Georgia, and in Brazil, Sao Paulo is our home. In total, we've got 22 factories around the world, 12 in the UK. Now, enough of the corporate speak, let's get into some engineering, shall we? Here we can see the historic process that we use for developing parts. The development cycle comprises a series of physical welding trials. For a completely new component or machine with new tooling, this can be up to 5 physical iterations. And in the physical iterations, we're looking to understand the weld approaches, specifying weld sequences, minimizing distortion, quantifying and agreeing realistic design tolerances with the design teams, and approving pre-production builds. This is all done physically, and in terms of a typical lead time, that could be 15 to 20 weeks. Oh, and I should say at this point, this can be done fairly late in the process, especially if we find that the design team make any late significant design changes. Anyone know this one? Anyone know this to happen? In terms of the scale of resources needed for our fabrication business unit in Pune alone, they developed last year over 300 parts. So there's a lot of physical testing for weld procedures and tooling, as you can see. And the main challenges are minimizing weld distortion, weld penetration, and agreeing weld tolerances with the design, distortion tolerances with the design teams, who generally specify the tightest tolerance possible. And the problems with such an approach based on physical testing is long lead times, reliance on physical trials, and of course high development costs. Now, in contrast with that, an optimized process using simulation at the heart of this could look something like this. Virtual weld trials are followed by a fewer number of physical trials. And in this methodology, optimization and iterations can be done earlier in the process with a much reduced lead time and at a fraction of the cost. Benefits that we have seen are a significant reduction in lead times, 25 to 35% reduction in lead times, 60% reduction in physical trial reduction, and approximately 50% reduction in development costs. Okay, so the welds analysis, if we do it in simulation, allows fabricators to understand some of the following. You can see them on this slide here. Optimum clamping, allowable tolerances, weld distortion, optimizing the weld sequencing, understanding locked-in residual stresses, and also predicting the effect of any post-weld heat treatment if it is being specified. And of the capabilities, the most valuable ones for us right now are being able to project weld distortion and weld penetration. And I've tried to draw that out in the 4 case studies that follow. Right, going back to basics then, and this is the same for all weld process simulation. For anyone that hasn't done any weld simulation before, these are the steps that we go through. First thing is you need to import into your software 3D CAD geometry, including the weld. That geometry is then meshed, and you have to define the weld sequence and the weld parameters. Those welding parameters are typically voltage, current, and travel speed. You have to define the boundary conditions, so this is related to the tooling and your fixtures, and then you press the solve button and wait for the results to come out. So let's look at the first of our case studies. This is a chassis from a machine. It's a front chassis, and in this instance the axles mount here and here, so we've got a tolerance on the gap that we've got. Unfortunately, and as you can probably all imagine, when we weld this up, this gap wants to close. Now, in order to fit the axle and maintain the tolerance, the chassis was jacked out. And guess what? This causes cracks to appear. And those cracks are in this joint just here. And unfortunately, this was found very late in the design and the development process. Now, experience showed that there would be deformation, but this simply could not be quantified until we had a physical prototype. So we have a chassis distortion of about 7 to 8 millimeters in reality. We created a model. We defined the weld sequence, and it's maybe not clear on the slide, but you can see each one of these is a weld, and this is when they are applied in sequential order. And we actually got a prediction of 7 millimeters distortion in simulation, which ties up very well with reality. Now, the virtual optimization was done, and we showed that a 6 millimeter preset on the chassis legs before weld would in fact give a 0 offset. Physical trials were then conducted, and we noticed a 1 millimeter distortion against acceptable limits. Case study 2 is a classic for us, really. Most of our components are connected via pin joints with a pin and a bush going into a pre-machined boss. To allow that boss to fit properly, the bush to fit properly into the boss, and to ensure even wear of the boss and the pin in service, we do maintain tight micron level tolerances on ovality. Pre-machining that boss also allows us to reduce production costs by eliminating any post-machining. Here we can see the ovality tolerance and the actual ovality achieved. Perhaps not surprising, as there is a lot of weld around the bosses, but no amount of experience would allow a welding engineer to predict the actual distortion in this case. The predictions of the as designed model correlate very well, and the solution was found and validated in simulation. In this case, the solution was to increase the boss wall thickness from 7.5 millimeters to 10 millimeters. And these are the final results that we got, well within the 70 micron allowable limit. And this case study has shown how we can get acceptable correlation and validate a solution without relying on those expensive, time-consuming multiple physical weld trials. This case study is where we've got a very large chassis, and right from day one it's always been welded in a single fixture. However, there was a proposal to make it into 4 main sub-assemblies and then bring it into a final welding fixture, and that really gave us a lot of operational flexibility. But before committing to the expense of tooling trials, simulation was done to optimize those weld sequences and reduce distortion, and to build the business case before investing any physical resources. As you can see, the correlation of the model was between 70 and 80% of the final measured deformation. And here on these last 2 images, you can see a few of the welds that were changed to minimize the overall distortion. And a key point to raise here is knowing which welds contribute most to the overall distortion. That's of great value, and in particular that's highlighted in the next case study. The final case study was for cab. Now, our factory in the UK produces cabs. This particular example is from a wheeled loading shovel. There was an issue with the door fitting poorly as a result of weld distortion, and this was found during assembly when the door was being fitted. We did the simulation, and as you can see, the correlation isn't fantastic in terms of absolute deformation. However, the behavior is correct, and the correlation was still good enough to find a solution. So 66% correlation, but the overall behavior was right. It matched what was happening in the field. The solution was found by changing the weld sequences and putting the back panel that you can see highlighted here into a separate sub-assembly, thereby reducing the distortion by 45%. In this particular instance, we've attributed the relatively poor absolute correlation to the large number of welds in this model. In this case, there were around about 200 welds, where in some of the other case studies that you've seen, we've had less than 50. Now, in summary, the simulation is generally used for distortion and weld penetration assessment. There are significant time and cost savings to be had. Directionally, the correlation is very good, but the simulation does tend to underestimate the deformation. Where we do get variation, it's thought to be related to piece part fit up not being modelled up, and also variations in the physical weld size, etc. In terms of the estimated business benefits, we've summarised these on this page. We've seen approximately savings in development time around about 30–35%, certainly feasible. 60% physical trial reductions, definitely, and a bit of an estimate here, but probably a 50% reduction in development costs is realistic. On the challenges side, there are still some challenges to be faced. One is because you have to model in the welds, and there can be a lot of welds. If you look at the example of the cabin, for example, there can be a long meshing time. There can also be long solve times, although developments in high performance computing and cloud computing may well mitigate that. We need to improve some of the automation of non-productive, non-value added setup time in the software. And also literature on thick wall welding we found is relatively limited. There's a lot in the thinner wall stuff, maybe lends itself more to the automotive industry, but in our industry, in that sort of 6 to 12 millimeter, maybe 15 millimeters, there's limited literature. And that is what I've got planned and prepared for you this morning. At this stage, I'm more than happy to have a discussion and to get some feedback from your good selves. So thank you very much.
Okay, thank you, David. That was a really great, fascinating presentation. I really like the practical examples and case studies that you showed to us. It's great to see the comparisons with tests, but also the ways in which simulation was clearly able to demonstrate the solutions worked. And especially liked how you were able to actually show and quantify the business benefits of simulation. Now, we've had a few questions already submitted, but please do keep them coming in. We've got a bit of time to be able to answer all the questions that you've got. So turning over onto the first question, how practical is the application of simulation to low volume but high integrity, highly welded, heavy duty structures? For example, we've got total production run of 10 to 12 units and a thickness of 10 to 50 millimeters.
Yeah, well, I think it's absolutely practical, definitely for those sort of structures. That is more of a commercial business type decision, payback decision really, and how much time is spent reworking things or getting the weld procedure right in the first place. Certainly, from our experience, you can do it. I wouldn't have any issues with it at all.
Great, thank you. So the next question would be, how do each inputs, voltage, current and speed, affect the weld? Okay, well that's a good question. I am not a welding engineer in itself, but we change the welding parameters depending on which part of the structure we're looking at. Certain parts of the structure which are more highly stressed, we will be wanting a lot of deep penetration, in which case we'll put some more energy in and possibly slow the weld down.
In other areas where weld penetration is less of a concern, we might speed things up and put in less energy. But the great thing about this tool is that we don't have to do the trials and errors, and we're not relying on experience to do that. We can get much closer to the end solution by doing the simulation. Now, one of the things that we do face as an industry is the shortage of skills. And while a lot of people, some very experienced welding engineers here at JCB, can look at a structure and say, oh yeah, that's going to distort by 15 mil in this direction, the reality is a lot of these guys and girls are going to be retiring in the very near future. And we need to be able to share this knowledge with the younger generation of manufacturing and welding engineers. And that's one of the benefits of being able to play different scenarios. But you can change all of those parameters, not a problem.
Great, thank you. Yeah, so we've got a lot of insight through simulation. How important is weld pen? Do you aim for full, or is that overkill?
Well, that absolutely depends on which part of the structure you're looking at and whether or not it is highly stressed. We will do the structural simulations to understand where those high stress parts are, and in that case, yeah, we do ask for full penetration, and that will be an absolute essential. In other areas, or non-highly stressed brackets, for example, then the weld penetration is less of a concern for us, really.
Great, thank you. What sort of simulation were you using to perform your distortion analysis?
I wasn't sure what that, I did see that question come in a little bit. I wasn't sure what sort of simulations people were asking about. I mean, we're using off-the-shelf software. I know there's other different flavors of software available, but we're using a tool called SysWeld. And that seems to be giving us good results. So if there's any more information about what different simulations people are asking about, I'd be happy to comment.
Actually, okay, yeah, we've got a reply from the questioner on that. So I suppose, I mean, whether we're using heat input thermal mechanically sequentialed couple models or a more simplistic method on linear elastic strain or another method.
We are using heat input thermal mechanically sequentialed coupled models, I believe, and I wonder if Nankishore has a bit more information about that at all.
Yes, sir. We are using thermocouple coupled analysis for this one. Actually, basically, this is the two type of analysis. This is the one is a transient based analysis, and this is completely depend on the temperature versus time. We used to consider the travel speed there, and second analysis is the shrinkage based analysis. That's is a very shortly we can do it. It's not time dependent analysis. This is the two basic type of analysis we are doing.
Great, thank you. So move on to next presentation. Next question, sorry. Thanks for your great presentation, the question says. I've been using SysWeld and computational time is a big restriction. How do you overcome the solving time for such a big size of component?
Well, yeah, that's a very, very relevant question, and it's something that we are looking to address. Obviously, it does take a long time to solve the more complex, bigger models that we've got. Longer term, looking to the future, then we'll be looking at probably cloud computing as being the big next step for high performance computing, rather than have our own dedicated data center.
Great, okay, thank you. So can simulation look at PWHT and preheating?
Yes. In short, yes. It's not something that we have used much at the moment. We do use some preheating and we do some post-weld heat treatment, but we try and avoid it from a logistics and operations perspective wherever possible. There is a short answer, yes, but we're not using it at the moment.
Okay, the question about the applications is, are the weld simulations unlimited to MIG welding, or can they include other types of welding like laser, ultrasonic, spot welding, etc.?
I'm going to ask Lancashire if you know the answer to that.
We can go with the other type of the welding also here. Definitely we can go for the laser hybrid, spot welding also we can do. I'm not very sure about the ultrasonic, but the laser and spot welding we can do it with this simulation.
Great, thank you. So the next question would be, are 3D moving heat source models used for welding simulation?
3D moving heat source. I mean, this is a 3D moving, it's a 3D model and the heat source is moving. So yes, I hope that answers the question. If not, then please get back to me.
David, actually just like to answer with this one. We are not simulating here the weld pool exactly, but we are simulating the heat pool. That is the transfer with respect to the time. But exactly, if precisely say weld pool, we are not simulating here.
Okay, thank you both. So how many personnel are in the team for one analysis in total?
Well, Santosh is our team at the moment, who's been producing this initial work. But we do have a design center based in Pune who do simulations for us across JCB, and that is typically sort of 14 to 16 people doing simulations for and that's linear static, non-linear static, FEA, but also they have the capability if Santosh wants to outsource some of that work.
Great, okay, so we're quite a good sized team.
But I do see this growing going forward.
Great. Are there any other major limiting factors with software used for the simulation? I
would say the computing power, as we discussed earlier on, is the main one. Lancashire, Santosh, is there anything you'd like to add in terms of limitations?
If you talk about the limitations for this particular software, I think the pre-processing time which is required for model preparation is quite large at the moment. And when I say about pre-processing, the main time is consumed in creating the mesh for the model. So when we are going for 3D models, we need a mesh with hexahedral elements and with node-to-node connectivity. So that is the issue that we face. We need more time for creating that mesh mainly. So that is the main challenge I see.
That's great, thank you. And actually, there's a question submitted that's perhaps a follow-up to that or linked to that. Could you say what would be a typical mesh and solve time for something like the front subassembly and setting the larger structure?
Santosh, Lancashire, that's an ideal question for you.
Which type of mesh? Which type of mesh we are using? For 3D models, wherever we are preparing the mesh for the weld regions, so we are using hexahedral elements, which are typically 8-noded hexahedrons. And as and when we move away from the weld, we can use maybe penta or tetra elements also. But it is a requirement that for weld we need to model with hexahedral elements only.
Okay, thank you. Do Do you see any way to improve the process with new technologies?
Where we are in terms of our evolution, it's really about increasing the adoption of the existing technology and really embedding it in our new product introduction process. That's our immediate challenge. New technologies and improving the process, that's probably where we would look at organisations like TWI, for example, to help us understand what new technologies, and also the software vendors themselves.
Great, thank you. Is there any form of calibration that's needed in the software to ensure an accurate heat-affected zone prediction, such as measuring the welds?
Sure. Santosh, are you able to comment on that?
Yeah, we do have a calibration with the actual process to the software, but not exactly the heat affected zone. We have calibration with respect to the penetrations, because that is the main parameter we are looking forward in a process. Heat affected zone is quite near to the metallurgical point of view we are looking at. So we have established some correlation with the software and the practical. So we can adjust some heat input with respect to the calibrations. That calibration is totally depend on the which type of weld we are doing. So that we have did all calibration during the analysis.
Great, thank you. Question about the material model. How accurate is the material model? For example, is the hardening law and are any phase changes accounted for?
Well, that's not something that we've gone into a great deal of. In terms of material models, you can really delve into this. You can write PhDs on it. What we found is that sort of getting the accuracy to within sort of 80–90% accurate is sufficient for us. If we really wanted to drill into the extra accuracy, if that was really, really critical for us, then we would be looking at material models in a lot more detail. And yeah, I think that came from someone at Rolls-Royce, wasn't it?
That's right, yes.
Yeah, so I'd probably be on the phone to them to ask for some help.
Yeah, a lot of expertise there.
Sorry, on the materials, again, thanks, sure, Santosh, is there anything that you wanted to add on that? Have we lost them?
We can define the material of component and whatever the well filler we are using. We can define, but it's not that accurate actually, as the question is raised there. But definitely there is a possibility we can define the material of the particular component. So even though if we have different material in particular component, we are able to define that.
Yeah, but we've not spent a lot of time looking at optimizing those.
Okay, and sticking with materials modelling, are relevant materials property data readily available, and how susceptible are the models to small differences in material properties?
We don't really know how susceptible the models are to the material properties. Like I say, because we've found some initial ones very, very quickly that we found worked and gave us answers to what we needed. We don't necessarily need to be anything more accurate than the examples we've presented. The relevant material property data, is it available? You know, it's like a lot of materials data, it's not always readily available, is it? It's quite often it's tucked away in people's drawers.
Yeah,
and I think that applies to any form of simulation. I think, you know, if you're doing non-linear static analysis, we've got exactly the same problem.
Absolutely. Yeah, it's my goal is getting the right materials properly. um, can the program indicate the location and level of residual stresses?
Yes. Yes. So we do know that residual stresses can have a significant effect on the performance of a structure in fatigue of that welded joint. And being able to visualize those residual stresses can have some benefits for us. So, for example, if we knew that a part of the structure was highly stressed and we were predicting low fatigue lives, but from the residual analysis we knew that it was highly compressive, then that might allow us to take a slightly more relaxed approach to it and accept those higher stresses. Equally, if we knew that the residual stresses were extremely high, then we would be more cautious in accepting that.
Brilliant, thank you. And are you able to investigate the effects of stress relief using a heat and oven process to understand the effects in distortion mitigation in the software?
Nangshu, I think that's a question for you.
Yeah, actually, we have capability to apply the post-weld heat treatment after seeing the residual stresses on component, and definitely we can see how much benefit we can get from that. So the simulation perspective definitely is there. We have trying to establish this process to look at the advantage of the heat affected to reduce the residual stresses by applying the post-weld heat treatment.
Great, thank you. Now, you touched on your presentation in terms of comparisons with tests, but the question is typically what would be the percentage difference between reality and simulation? And during the simulation, do you include the welding seam?
Sorry, Tim, could you just repeat that question for me, please?
So I think it's two separate questions. So the first question is typically what would be the percentage difference between reality and simulation?
Okay, so I think typically I would say about 75% with the simulation, based on the parameters that we use and the material models that we use, underestimating what you see in reality.
Okay,
but
great.
That is a really rough finger in the air answer.
And I think that's what the question was after. So yeah, it's great to give that sort of level of answer. That's great. And then, yeah, the second part is, during the simulation, do you include the welding seam? And if you do, how do you estimate the seam thickness?
So yes, we do include the welding seam, and we will, in terms of the initial design, that will be based on structural calculations. So the stress engineer that's doing the linear static structural analysis will be specifying what size welds that they want. Does that answer the question, do you think?
I think so, yes. But yeah, if the questioner wants to, when he sort of follow up to that, that'd be great. But yeah, that sounds good, thank you. So moving on to the next question, this is something I want to ask actually, but what kind of loading is given to the cabin to check the weld strength?
Okay. Cabs are easy. Cabs are the one component on the machine which is dead easy for us because we are driven by, because it's an operator safety enclosure, there is a clear legislative guidance on the tests we need to complete. So we strap the cab down to the floor, and then we provide a side load, which is specified in the standard as a multiple of the machine mass. We then apply a rear load, and then we apply a crushing load. So we put a beam across the top, and we pull it down. And so from a physical test perspective, the parameters are very clearly understood. And from a calculation perspective as well, we know what the boundary conditions are, which does not happen very often in our industry, I have to say.
Yeah, I mean, that was what I wanted to ask myself I mean, you see your machines being used on construction sites and subject to all sorts of abuse. So how do you come up with the appropriate loading scenarios, and what sort of confidence do you have that you're able to predict what the loading is?
Okay, well that is what keeps me interested, and that's why I love my job, fundamentally, because we have so many different machines as well. I often say to our automotive cousins, I don't know if we've got many automotive people on the line here, that they've got it easy, because if you take a Mini and then you take a 3 Series and a 5 Series and a 7 Series, fundamentally the load inputs are pretty similar, and there isn't very much geometry movements. Yes, there's some movement in the suspension, and there is some steering geometry, but that's very different from the degree of movement that you would get from an excavator arm, for example, that was digging through the soil. When it goes into the ground, it's reacting against the loads. When it comes out, it's reacting against the mass and gravity and the weight in the bucket. So we have some standard load cases. So they will be based on hydraulic loads and machine stability loads, because a lot of our machines are designed, you dig up until the point at which the rear of the machine lifts off. And then we go through the physical testing, and we'll do some strain gauging and predict fatigue lives from that strain gauging, and we'll do some rig testing. But over the years, we've been able to correlate our simulation models with the field testing. So that's really how we've optimized our load cases. We do go out and put load cells in certain parts of the structure, but it's a fascinating subject. You could spend a whole lifetime trying to understand what the loads going into these structures would be.
I can well imagine. Okay, so coming back to the details of the welding, do you run simulations with the groups that perform the welding to understand how the welds themselves are formed, such as porosity formation, and use that in the larger FEA model?
No. To date, we've not looked at that. No.
Okay, that's great. Yep.
We're assuming that we don't have any significant defects.
And how does the simulation account for manual welding speed changes rather than consistencies of robot welding machines?
You can, if you want, change the speed. You could, I imagine, do a bit of a statistical analysis if you wanted to, looking at the statistical likelihood of welders speeding up and slowing down throughout the length of a weld. But I don't believe we have looked at different welding speeds due to manual operation. Nankishore, is that correct?
Yeah, it's correct. With robo, we can play with the travel speed, but manual, we have limitations.
Okay, great. So how are the material properties and behaviour accounted for within the simulation, and how much flexibility exists to use specific materials and understand effects of PWHT?
Tim, I'm sorry. I was reading another question as you read that out to me.
Sorry. How are the material properties and behaviour accounted for within the simulation? And then the second part is how much flexibility exists within the simulation to use specific materials and understand the effects of PWHT.
Well, we do have complete control over the material properties. So at the moment, we've been using some fairly standard material properties, but you do have a very wide-ranging set of material parameters that you can put in to change those.
Okay, lovely. You were mentioning in your talk about the automotive industry and how you read across from that. And this question is, what are the significant differences in welding challenges facing the construction industry compared to the automotive industry? And how can simulation help to overcome these challenges?
I think the first thing is the sheer number of different fixtures that we need for the types of components that we are producing. We have a much broader range of geometries and types of components. So we've got a product range of around about 350 machines, may well be more than that now. Those are falling into a number of different categories, so probably about 7 or 8 different machine types, and even within them we can have different chassis. So the spread of components is broader. The materials that we're using, fundamentally steel. The gauge of the materials that we're using, so typically sort of 6 to 15 mil, although we do go up to 50 mil, which is possible. And spot welding isn't something that we do very much of, really. Spot welding's not really much use to us, given the gauges that we're looking at. I think, is there anything else that I've missed off, Nankishore, that you think you can add?
Actually, the major change is we are using on higher thickness side, and automotives are very thin sheets they are using. So that's the main difference, and that makes a challenge to us, because as we are using the higher thickness, heat input is very high as a welding concern, and that making challenges to do the meshings and that all activity. As we have initially spoke about the challenges with the meshing and same, that is the challenge we are facing, because we are using the higher thickness of the plates in our industry.
Great, thank you.
Yeah, I think that pre-processing and geometry preparation side of things is probably more significant for us as well.
Lovely. Coming back to residual stresses, are residual stresses from the welding considered for subsequent stress and fatigue assessments?
At the moment, we rely for our fatigue assessments on BS 7608, which is the fatigue life prediction code for welded structures, and that assumes an inherently high tensile residual stress of yield, order of yield. If we wanted to, we could start looking more and more at residual stresses and say, well, actually, the residual stress isn't as high as that assumption, and therefore we could take a slightly more relaxed approach to some of the stresses, if that makes sense.
Yeah, thank you. Moving on to the next question. With regard to the materials that you use, have you investigated the use of thinner sections of higher strength steels to reduce the overall weight of the machine and thus to lower fuel costs?
Right. Another big difference between us and automotive is that in automotive, every kilogram that you take out of your structure is a good kilogram from a fuel economy perspective. That's not the case for us, because if you take weight out of the structure, out of the machine, then it becomes less stable and it's more likely to pull itself into a hole, or it's not able to lift as much. So we have this sort of balancing act. Some parts of the machine, it makes sense to take weight out. So if you imagine the extremities, so the near the buckets, that makes sense. But then quite often we end up putting weight back into somewhere else to maintain stability. But yes, we could look at using, this could be a tool that would help us try and optimize our structures. Generally, we don't use a lot of high strength steels, predominantly because we're governed, there's no point, because we're governed by the fatigue life and the fatigue strength of the welds. Unless we can find another way of joining the steel without the welds. If, however, we could do some simulation and understand the effect of residual stresses, then we might, yes, be able to use thinner gauge steel and accept higher stresses. The other option is doing post-weld heat treatment, stress relieving, which we know can be very, very effective, but it comes with a cost. There's that balancing off. You know, do you want to go with thinner material that maybe costs more, and you're putting in a post-weld heat treatment effect? So we don't have that absolute driver that the automotive and the aerospace industries have for taking weight out.
Lovely, thank you. And just, there was a question there relating to the post-weld heat treatment. Do you do any post-weld heat treatment or peening to improve the fatigue life at limiting locations?
Not peening. Post-weld heat treatment, yes. There is some that goes on, although we try and design without it. I think one technology I think TWI have spoken to me about in the past is ultrasonic impact treatment for treating the toe of welds. And if anybody wants to contact, anyone knows anything about that and wants to reach out to me after this, I'd be happy to have a conversation with you.
Okay, we've still got lots of questions coming in. I'm afraid we're not going to get to them all because time is running out. Perhaps make this the last question. Do you carry out weld uncertainty quantification for strength or fatigue?
Do we carry out weld uncertainty quantification? No. What we do use is the guidance in BS 7608, which takes an inherently statistical approach to predicting fatigue life, because there is a huge scatter. There is a very big scatter. So we use the parameters that are defined in BS 7608.
Lovely, thank you. So, like I said, I think we're sort of running short on time now, so I'll start to draw this session to a close, but thank you everybody for all your questions, and please be able to get to answer a good number of them. And I'd like to say a big thank you to David and to your colleagues, Nancy Shaw and Santosh, for answering all those questions and for a really excellent enlightening presentation. And your products are so iconic and well known to all of us. It's been fascinating to hear about some of the solid, impressive engineering that helps to support the company and all the different products that you've spoken about. Before we go, I'd just like to remind you that there'll be a recording of today's session. It's going to be available on demand via the institution's website. So if you'd like to review it or to recommend it to your colleagues who might miss the presentation, please do look out for that. I'd also like to briefly mention and plug the fact that NAFEMS is hosting a conference dedicated to engineering simulation later on in the year here in the UK. It's going to be taking place on the 9th and 10th of November. We're hoping it's going to be based around a physical event in Milton Keynes. Whether or not it has to become a virtual event or some sort of hybrid mixture of the two remains to be seen. David is one of the members of our UK steering committee, and he and the other members of that committee are going to be making the decision about the precise format at the end of the summer. But please do look out for further announcements about that, the NAFEMS UK conference on engineering simulation on the 9th and 10th of November. And with that, I'd like to thank David and his colleagues once again. I'd also like to thank Emma and the team at the IMechE for organising this event, and to all of you for taking the time to with us and asking so many great questions. Hope you've enjoyed it as much as I have. I found it to be useful and informative. Thank you for your time and attention, and goodbye.